So yes, in this talk, I'm going to discuss an ongoing formalization project, which is joint work with Antoine Chambert-Loir. And I'm going to divide the talk into 4 different parts. So in the first part, I'm going to give some motivation of why we decided to formalize the divided power envelope. So depending on your background, the divided power envelope might be something that you have never heard of. So I want to give some motivation as where this shows up in number theory, why it is important, and why, if we need to formalize, if we want to formalize some important results from current research in number theory, this is something that we need to formalize first. Now, the second part of the project will be a brief overview of the project to give you an idea of the scope of the project and what we have already done, what we are still doing, and so on. And then in the main part of the talk, I'm going to talk about divided powers. And in that part of the talk, I'm going to start from the very beginning. So even if in the first part of the talk, the motivation from number theory is something that feels very different from the kind of mathematics that you are used to, the third part is going to be quite elementary. So you are not going to need any background in number theory to be able to follow that part of the talk. Okay, and then finally, for the last part, I also want to say a few words about the construction of the divided power envelope once we have already set up all of the basic theory of divided powers. Okay, so to give the motivation, first I'm going to start by reminding the definition of the p-adic numbers and the p-adic complex numbers. So first, we all know that to construct the real numbers, we start with the rational numbers Q, and then we take the completion with respect to the Euclidean absolute value. Now, it turns out that the Euclidean absolute value is not the only interesting absolute value that you can put on the rational numbers. In fact, for every prime number P, you get a p-adic absolute value, which I'm not going to define precisely here, but the slogan, if you like, is that for this absolute value, P is small, in a way that P to the n goes to 0 when n goes to infinity. Or also you can think of it as thinking that integers that are very divisible by P are very small for the p-adic absolute value. So I'm giving you some examples here. So if you look at the number 2 to the 10 times 3 to the 8 times 5 to the 4, so this is a number that is quite large in the usual Euclidean absolute value. However, if we look at the 3-adic absolute value for this number, well, that number is going to be determined by the power of 3 that appears in the number. So in this factorization, we see that 3 appears to the power of 8, which means that the 3-adic absolute value is going to be 3 to the minus 8, which is very small. And then conversely, if we have some big power of 3 in the denominator, then the absolute value of that rational number is going to be, the 3-adic absolute value is going to be quite large. Okay? So you can show that this function that I have not quite defined here is in fact an absolute value. So it satisfies all of the right properties for being an absolute value. And therefore we can repeat the same process. So we can take the completion of Q with respect to this new p-adic absolute value. And that is going to give us a different field. And this is the field of p-adic numbers. Okay. Now we've seen that QP is the p-adic analog of the real numbers. Then we can also wonder what is the p-adic analog of the complex numbers. If you think about how you construct the complex numbers from the real numbers, you can get them by taking the algebraic closure, right? So our natural first guess is assuming that the algebraic closure of QP is going to be the correct analog for the complex numbers. However, it doesn't have all of the right properties for considering it as a good analog. So it does have some properties that, in particular, it is algebraically closed just by construction, and you can extend the p-adic absolute value on QP to the algebraic closure, and you can show that this extension is unique. However, the reason why we don't consider this to be a good analog of the complex numbers is that the algebraic closure of QP is not complete with respect to the p-adic absolute value. Okay. Which is something that is true for the complex numbers. The complex numbers are complete with respect to their absolute value. So to get a better analog, we are going to take one extra step, and we are going to define the p-adic complex numbers, CP, to be the p-adic completion of the algebraic closure of QP. And now, by construction, this is complete for this absolute value. And you can also prove that this is algebraically closed. So it has the two properties that we wanted, and we can consider now this to be the correct analog of the complex numbers. Okay. So I'm introducing this because, well, in the p-adic numbers are widely used in number theory. The extension of fields QP-als over QP is something that we are very interested in understanding. This is an infinite extension of fields. You can consider the Galois group of this extension, which is the group of all automorphisms of the algebraic closure of QP that fix the field QP pointwise. And this is going to be an infinite group. And in fact, it is a group that inherits a topology that makes it into a topological group. Okay. So one way to try to understand this algebraic extension is to understand the Galois group. There are different techniques to try to get information about the absolute Galois group of QP, of this group GQP. And one of them is to consider Galois representation. So a p-adic Galois representation is going to be a group homomorphism from this group, this Galois group GQP to GLV, where GLV is the general linear group over some finite dimensional vector space over QP. So notice that in this setup that we have just defined, we have the same prime P appearing in the domain and in the codomain. You might also be interested in considering different primes in domain and codomain, but that's not what we are going to do today. Okay, so there's one sub-area of number theory which tries to understand this kind of p-adic Galois representation. Some representations that are especially interesting are those that come from geometry. So what I mean by that is that sometimes you can consider some geometric object, some variety defined over QP. So this could be a curve, or it could be a surface or something of higher dimension. And to this geometric object, you can associate certain cohomology groups. In particular, you can associate étale cohomology groups. And it turns out that these cohomology groups are an example of a p-adic Galois representation. So one natural question is, if I give you a Galois representation, can you determine whether this representation is of this form? Whether this representation actually comes from some kind of geometric object? This is something that there's a lot of research about. So Fontaine created some theory to try to understand these Galois representations better. What he did is he defined several period rings that can detect interesting properties about Galois representations. I'm not going to get into the details of how this works, but basically, if you have a p-adic Galois representation and you have one of these Fontaine period rings, there's some kind of computation that you can perform, and the result of this computation will tell you whether the representation has some sort of interesting property. So I will give you some examples of the kind of properties that you can detect. So the first examples of Fontaine period rings are two of the fields that we just discussed. So the first Fontaine period ring is just the algebraic closure of QP. And for this example, what happens is that Galois representation V is going to be admissible for the algebraic closure of QP if and only if the action of the Galois group of the absolute Galois group of QP acting on V factors through a finite quotient. Okay, so this is the first example of property. The second example is quite similar. Now we are going to take a bigger ring. We are going to take V to be the field CP of complex numbers. Then the representation is going to be CP admissible when now we don't have that the full action of the full Galois group factors through a finite quotient, but we can consider the action of the inertia group, which is some interesting subgroup of this Galois group. And in this case, the action of this inertia group on the Galois representation of V is going to factor through a finite quotient. Okay, so these are two concrete examples. The third example is the ring B-cris. So defining this ring B-cris is the end goal of the project that Antoine and I are working on. And this is one of the places where the ring decrease shows up in number theory. So we say that p-adic representation is crystalline if and only if it is admissible for this ring decrease, which I have not defined yet. Okay. Okay, so this is one place where this ring shows up. This comes up in p-adic cos theory, which is this area of number theory that tries to understand p-adic Galois representations. But there's also another application of these Fontaine period rings, and that has to do with cohomology theorems. So if you have a variety, again, some geometric object defined over a p-adic field, so over some finite extension of the field QP of p-adic numbers, then assuming that this variety is nice enough, there are several cohomology theories that you can study. So you can study the rank cohomology, crystalline cohomology, étale cohomology, and you would like to understand how all of these cohomology theories are related to each other. So in particular, the ring decrease shows up in a comparison theorem between the étale cohomology and the crystalline cohomology. So I'm not going to be very precise here, but essentially what this theorem tells you is that after tensoring with the ring decrease, the étale cohomology groups become isomorphic to the crystalline cohomology groups. And these isomorphisms are going to be nice in the sense that they respect the Galois action on both sides, and they also respect the Frobenius action on both sides. So they preserve some data about these cohomology theories. Okay.
Sorry, have you given a definition of B-cris, or is that something?
I haven't given the definition of B-cris yet. I'm going to do that in the next slide, but I want to warn you first about this definition. So the definition of B-cris first is very technical, and second is not needed for the rest of the talk. Okay, so the only reason that I'm going to show it to you for two reasons. So one reason is to show an example of a definition from number theory that is very complicated just to write down. Okay, and the second reason is because I want to show you all of the steps that go into the definition so that I can tell you which of them are already available in Lean or which of them are available in Mathlib. And also we will see that one of these steps is this divided power envelope that I'm going to discuss today. Okay. So yeah, but before getting to the definition of the ring, I wanted to justify that this ring is important. It gives us interesting information. It shows up in this area of p-adic cross theory that tries to understand p-adic Galois representation, and then it also shows up in this comparison theorem that relates to different cohomology theories. Okay. Okay, so now let's look at the definition. So these are all of the steps that go into defining the ring decrease. Okay. So the first one we have already discussed it. The first one is we need to start by taking this field of p-adic complex numbers. So I already told you how this is defined, and I already explained that this is an analog of the usual complex numbers. And this is something that I formalized in Lean a couple of years ago. The formalization of this field, well, to formalize this, I formalized some more general result about extensions of non-Archimedean norms. This full result took about 5,000 lines of code, and most of this code is available in Mathlib, but not all of it is in Mathlib yet. So we don't still have CP in Mathlib, but we have it completely formalized in Lean 4. And we expect that it will be in Mathlib soon. Okay. So the first step is done. The second step is once you have defined this ring CP, well, it turns out that this has this p-adic absolute value. You can also think of it as evaluation, and you can consider the ring of integers with respect to this absolute value. So this is this ring denoted to CP here. And then you can look at this inverse limit of these quotients, which I'm not going to define very carefully here because, again, this is not the topic of this talk, but this is something that is available in Lean. So in Lean, there is something called pre-tilt that will give you exactly this definition of this ring E. Okay. The next step, again, is available in Mathlib. Once we have this ring E, we can construct the bit vectors associated to it. So we can define this ring A-inf. This ring A-inf is one of the first steps for defining many of the Fontaine period rings, not only B-cris, but for example, it also is needed for the definition of another ring with a RAM. Okay, so we have that in Mathlib. Then in the same project where I defined CP, I also constructed a map theta from A-inf to CP. This is some kind of canonical homomorphism of rings. Okay, and now finally, this is where the divided power envelope is going to show up. So the divided power envelope is going to be some kind of universal construction associated to the ring A-inf and the ideal given by the kernel of this map set. Okay, so this step here in the definition is going to be the end goal of the talk today and the end goal of my project with Antoine. And then after you have this divided power envelope, you still have to take a few more steps, but again, these steps are available in Mathlib. So again, you have to take another PID completion, which is something that we can do. And then you will have to invert the element P in the resulting ring. And you will also have to invert some element T, which is an element in which the Galois group acts by multiplication by the cyclotomic curve. Okay? So really the only part that is missing to be able to define B-cris in Ling is constructing this divided power envelope. Okay? Okay, so that's the motivation. We want to define this ring B-cris. Now, let me give you a quick overview of the project. So I said we want to define this divided power envelope. Before doing that, we need to define the basic theory of divided powers. So we start with a ring A and some ideal I in this ring A. A divided power structure on A is a family of maps from the ideal to itself that satisfy the same properties as the family x to the n over n factorial. So I'm putting this in quotes here right now, but I'm going to make this very precise in the next part of the talk. Essentially, you want to take the family x to the n over n factorial, but this might not be possible if you are working in characteristic P, right? Because if n gets big enough, you will be divided by P, and this is not something that you can do, right? So instead of taking this family, you can take another family that satisfies the same kind of properties. Okay. And then we are interested on this divided power envelope, but as an intermediate step for this construction, we have to first define the universal divided power algebra. So this is something that you can define given any A module n, and it's going to consist on some ring, some ideal in that ring, and then some divided power structure on this ideal. Okay, and this construction will satisfy some universal property that we will discuss later. Then finally, once we have this universal divided power algebra, we can move on to the definition of the divided power envelope, which again is going to be some kind of universal construction that satisfies some universal property. I will show you the diagram that it fits into later. Okay, so the history here is that divided powers were first introduced by Cartan, but most of the results were proven by Robbie. And in particular, this construction of the universal divided power algebra, this is due to Robbie. And then the divided power envelope is due to Berthelot. Okay, so Antoine and I started working on this in the summer of 2022. And we started by looking at these two references by Berthelot and Auguste. Okay, so these are two books on crystalline cohomology. And both of them have a chapter that deals with the definition of the divided power envelope. So for reference, this chapter is about 15 pages in Berthelot-Auguste, and maybe a bit longer in Berthelot, because Berthelot sometimes gives more details in the proofs. But these two references have quite a big hole, and the hole is that this universal divided power algebra is not defined in this reference. So they are assuming that this construction already exists. They are basing their work on the previous work of Robbie, but they don't give you the details of the construction. So in fact, in this book by Berthelot and August, there is an appendix that gives you some sketch of the definition. This sketch of the definition is another 15 pages, and these 15 pages don't have nearly enough detail for a formalization of the construction. Okay, so things got complicated, and we had to go back to the Robbie original sources. So the main source is this article from 1965 that describes divided power algebras. But again, this is missing some details. So for some of the proofs that appear in this paper, we need to understand polynomial maps. And polynomial maps were studied by Robbie in this very long paper of over 100 pages, which luckily we don't need to formalize completely, but we need to formalize some parts of this paper to be able to complete our definition. Okay? So yeah, so these are many pages of mathematics that are needed just to formalize the definition of the divided power algebra. Okay, so now let me show you the import graph of the project. I will show it in here so that you can see it better. So maybe with the caveat that this is not the final graph that contains all of the details of the project. So in this graph, each of the nodes represents one file in the project, and then the arrows represent imports. But one reason that this is not complete is that some of the files that we have developed for the project have already been PR'd to Mathlib, so they don't show up on this graph. And then another reason is that there are parts of this project that are still ongoing work, so it is very likely that some of the files in the project might get split into other files later or something like that. Okay, but this will give you an idea of the big picture of the project. So the end goal is to formalize the divided power envelope. As I've mentioned before, the divided power envelope relies on the divided power algebra. So the divided power algebra is defined here as a ring, but then we have to show that this ring has divided powers, and this is done in this file. And to be able to get all of the results that we need to also show that this divided power algebra is a graded algebra. And for that, this is done in a few of these files. And for that, we also had to expand the theory that was available for graded algebras in Mathlib because it didn't have everything that we need. Okay, so that's the definition of the divided power algebra. Now, the part of the project that I'm going to focus on today is this basic part. So all of this is already completed. So here we have the definition of a divided power structure. Then we have morphisms and sub-objects for these divided power structures. And then some examples, like, for example, putting divided powers on a rational algebra or on a sum of ideals. Okay, so I'm going to focus on this part of the project. But before doing that, let me also show you this part of the graph. So this part contains a lot of prerequisites that we needed to develop. So some of the results that we needed are about weighted degrees for multivariate polynomials, and those have already been incorporated into Mathlib. But then we also needed results about evaluation and substitution of multivariate power series. And for that, we needed to develop the topology on the multivariate power series ring. So these are things that are currently being PR'd to Mathlib. And then here on this side, you can also see that we needed to develop some theory of polynomial maps coming from this 1963 paper of Robbie. So this is done in these files here. Okay. Okay. Any questions so far? Okay. So now things are going to get easy because we are going to go back to the basics. Okay. So we are going to go back to divided powers. So I told you before that divided power structure is a family of maps that behaves like the family x to the n over n factorial. So being more precise, this means that it is going to be a family of maps from an ideal I to the commutative ring A containing this ideal, indexed by the natural numbers, that satisfies these 7 properties. Okay? So these properties are just the properties that you will expect the family x to the n over n factorial to satisfy. So for example, the first property is that gamma naught of x has to be equal to 1. This is because x to the 0 over 0 factorial is equal to 1. Similarly, gamma 1 of x is equal to x because x to the 1 over 1 factorial is equal to x. The next is that whenever we have a positive n and an element of the ideal, then the image is also going to belong to the ideal, which is again clear from for the family x to the n over n factorial. And then we also want to understand the properties that need to be satisfied for when you add up two elements of the ideal, or you multiply an element of the ring and an element of the ideal, or you add up two natural numbers, or when you compose two of these maps. Okay, so this would be easier to do if I had a board, but for example, I'm showing one of the computations here, and then all of the others are done in a similar way. So you expand what happens for the family x to the n over n factorial, and then you abstract it to get the corresponding property for the family gamma n. Right. So for example, here, if I look at x plus y to the n over n factorial, I can expand this power using the Newton expansion, right? So this will be the sum over I and j adding up to n, or of n choose I times x to the I times y to the j. So if you expand n choose I, you get these cosine factorials. So n factorial cancels with the n factorial in the denominator, and then you rearrange and you get this one. Okay, you get this sum. So then going back to the general family, we see that we are asking for exactly the same. So if we apply that family to the sum, on the right-hand side, we want the same kind of formula that we have here. Okay. And then for the three remaining properties, you will do the same thing. You will do the computation for what happens to the family x to the n over n factorial, and then you will replace that family by gamma n, by a general gamma n. Okay. Okay, so now let me show you the formalization of this. So this is how we wrote up divided powers in lim. And I want to point out some technical detail of the implementation here. So in this slide, I'm saying that the divided power structure is a family of maps from the ideal I to the ring A. However, in the implementation, I'm codifying this as a family of maps from A to A. And then I'm saying that if I have an element of the ring which is not in the ideal, then the image is just going to be 0. Okay, so I am taking this map from this slide, and I am expanding it by 0 outside of the ideal I. And the reason for this is that since lim is based in type theory, so that means that every time has a unique type, if I put the ideal here, then I'm able to think of this element of the ideal as an element of I, but for that I have to use some kind of coercion map. And that means that you have to deal with coercions everywhere, and things get annoying. So to avoid having to deal with coercions, we are defining this as a map from A to A, and then we just ask that outside of the ideal, this is just 0. We don't care what happens outside of the ideal. Okay. And then the 7 remaining properties are just a translation of the properties in the first slide. Okay, so for example, if x is in the ideal, this is saying that gamma 0 of x is equal to 1. If x is in the ideal, gamma 1 of x is equal to x. For example, if I have x and y in the ideal, gamma n of the sum is this sum that we saw before. So this anti-diagonal n, this is going to be the pairs I, j that add up to n. So we are taking the same sum as before. And then maybe the other thing that is a bit weird here is this uniform bell, but that is just the Mathlib name of this portion of factorials. Okay. So the only difference with the definition that I showed you before is the domain of the map, but other than that, we just copy the conditions. Okay, so I want to discuss some of the basic results that you can prove about divided powers. So first I want to start by giving some examples. So the first case that we are going to consider is that if A is a Q-algebra, then the family x to the n over n factorial makes sense, because over a Q-algebra you can divide by n factorial always. And it turns out that this is actually the only divided power structure that you can put in the Q-algebra. So yeah, let me show you the definition we need. So I started by defining this of invertible factorial dot dpal. So this is going to be a family of maps from A to A interstate natural numbers, which is precisely given by this formula. Okay, so if x is in the ideal, then I send x to the n over n factorial, and otherwise I send x to 0. Now, you have probably seen that I haven't written here any hypothesis that the factorial is invertible in A. And that's because this definition of inverse in Mathlib is defined in such a way that if the element is invertible, it's going to give me the inverse. If the element is not invertible, then this just gives me 0. Okay? So this only gives me the right thing if I am in a situation where the factorial is invertible. But to write down the definition, I don't need to impose that condition. I will need to impose it later to prove results about it. Okay. So yeah, so we did this in more generality than just for a Q-algebra, and you will see why in the next slide. But for now, let's assume that there is a Q-algebra. Then we put this divided power structure on A. So we are going to say that our family of maps is this family that we just defined, x to the n over n factorial. And then, of course, to complete this definition, I have to provide proofs of all of the properties. But in this case, that's going to be quite easy because, after all, the properties of the divided powers are modeled after the properties of the family x to the n over n factorial. So you would expect that this is going to be relatively easy to formalize. Okay. And then this theorem is the uniqueness statement. So this is telling me that if I have any divided power structure on the rational algebra A, then that has to be equal to the one that we just discussed, x to the n over n factorial. And this is quite easy to prove. Okay, so why did we do this in more generality than just for algebras? Well, because this is also useful in this other case where we start with an ideal I in a ring A, and we assume two conditions. So the first condition is that n minus 1 factorial is invertible in A, and then the second condition is that the nth power of the ideal is equal to 0. So under these two conditions, then the family x to the n over n factorial is again going to be a divided power structure on the ideal I. Okay? Because essentially, the fact that I to the n is equal to 0 guarantees that you are never going to divide by something that is not invertible, because in the denominator, you are at most going to have n minus 1 factorial, and you are assuming that n minus 1 factorial is invertible. Okay? So we prove this in this setting, and then we specialize it to two particular cases. So one case is if you are working in a ring of characteristic P, and you have some ideal such that I to the P is equal to 0. Well, in that case, P minus 1 factorial is automatically going to be invertible in that ring. So that means that we can apply this more general case. And the other case is also if you start with some ideal whose square is equal to 0, then again, 1 factorial is invertible anywhere. So you can apply this result to get the divided power structure. Okay? Okay, so these are some examples. Now, I'm going to define morphisms and sub-PD ideas. So morphism, a divided power morphism, is going to be a ring map from A to B. So for this, I'm assuming that A and B are two rings where I have divided power structures. So I have a divided power structure gamma on an ideal I. I have a divided power structure delta on an ideal J. So a divided power morphism is a pre-nomomorphism from A to A, such that the image of the ideal I is contained in the ideal J, and such that these divided power structures are compatible, meaning that delta n applied to fx is always going to be equal to f applied to gamma n of x for any element x in the ideal. Okay? So yeah, we formalize this definition as is-dp-morphism. So we take the two rings A and B. We actually wrote this for semi-rings because it applies in that case. And then we take the two ideals that have divided powers, hi and j. And then we say that a ring homomorphism from A to B is a divided power morphism if it satisfies the two properties that I just told you. Okay, and then we prove some basic results about divided power morphisms. So one of the first things to prove is that the composition of divided power morphisms is again a divided power morphism. Another useful property to check is that if you have an ideal I that is generated by the span of some set S, and you want to check whether something is a divided power morphism, then it's enough to check the compatibility on the elements of X or of S. You don't have to check in the whole idea. Okay. Now let's think about sub-divided power ideals. So if you start with a divided power ideal I with divided powers gamma, we say that a sub-ideal J of I is a sub-divided power ideal if gamma n of X belongs to J for all n positive and X belonging to J. So we formalize two versions of this definition. So one is the propositional version, is sub-dp ideal, and the other one is the bundle version. So this is the version where we put together the data of the ideal and the proposition that the ideal has to satisfy. And both of these are useful, so we formalize both of them and we use each of them for different settings. Okay. So it's quite obvious that if you have a sub-divided power ideal of I, it inherits a divided power structure. And this divided power structure is just going to be the restriction of the divided power structure I. Meaning that for an element X in J, you just take d power n X, and then if the element is not in J, you just send that to 0. Okay, and again, there are dots here because you have to prove that this has all of the right properties, but this is very easy because this is just a restriction. Okay. And then another result is that if you have some ideal J and some divided power ideal I gamma, then the intersection of J and I is not always going to be a sub-divided power ideal. It is precisely when the divided powers are compatible mod J. Okay, so meaning that if you take two elements A and B that are in the ideal I, and the difference of these two elements is in the ideal J, then for this to be a sub-dp ideal, what you need is that you always have that the difference of the divided powers d power n A and d power n B also belongs to the ideal J. Okay. There are two more slides about sub-dp ideals. So the first one, again, is for simplifying proofs. So if you want to check whether the span of some set is a sub-divided power ideal, it suffices to check the condition of the generators. We provide this theorem as an if and only if. Of course, one of the directions is completely trivial because if you check the condition in all of the ideal, then it's obvious that the condition is going to be true in the generators. For the opposite direction, you have to apply some induction argument. Okay, and then we also prove that if you have two sub-divided power ideals, then the sum is always going to be a sub-divided power ideal. And also the same happens if you take an arbitrary sum of divided power ideals. Okay, and finally, I have two more results. The first one is about the connection between sub-divided power ideals and divided power morphisms. So if you have a divided power morphism from AI gamma to BJ delta, then you can check that the span of the image of the ideal I is a sub-divided power ideal of J. And also that the intersection of the kernel of F and the ideal I is a subdivided power ideal of I. So we prove these two results. Then the last thing that I will say about subdivided power ideals is that if you take any ideal J of A, then the product of I and J is always a subdivided power ideal. Okay. So we are proving these things, well, first to develop the basic theory of divided powers, but also because these are needed later in the construction of the divided power algebra. Okay, so yeah, so we need these results about subdivided power ideals. We also need to understand divided powers on quotients and divided powers on sums of ideals. So first, for quotients, we have two results that are more or less the opposite of each other. So for the first one, we are going to start by assuming that there is a divided power structure on this quotient, A mod J, specifically on the ideal generated by I in this quotient. And we assume that this divided power structure is such that the quotient map is a divided power morphism. In that case, the intersection of J and I is going to be a subdivided power ideal of I. Then we also provide a converse to this. So if you start with assuming that the intersection of J and I is a subdivided power ideal of I, then you can construct a divided power structure on this quotient such that the quotient map is a divided power morphism. Okay. Okay. And then we need also divided powers on sum of ideals. So if you take two ideals, I and J, both of them with divided powers, and you assume that the divided powers agree on the intersection of I and J, then the sum of these ideals has a unique divided power structure that extends the divided power structures on I and J. Okay. Now I'm copying the formula here. So I'm not sure if this is too easy to read given the lean syntax that we are using, the expansion extend. But basically this is defined to satisfy the formula for addition in divided powers. So remember that we had this condition that gamma n of x plus y has to be equal to this sum of gamma n of x times gamma n of y. Sorry, gamma I of x times gamma j of y, with I and j adding up to n. So that's exactly what we are asking here. So we are taking sums for an element A, which is in the ideal I, and an element B, which is in the ideal J. We are defining the divided power structure by that sum that I just described. So this is just forced by the definition. So if you want any hope that this is going to be a divided power structure, you have to define it like this. And then we prove that this satisfies all of the right properties. This proof is quite annoying to formalize because you have to switch the order of sums several times, and this is not always nice to do in Lean, but we got it done. And then we also prove that this is the unique divided power structure that you can put on the sum of the ideals, such that it is going to be compatible with the divided power structures on the ideals I and J. Okay. And then we also prove that for this divided power structure that we have defined on the sum, if you look at the identity map on A, that is going to be a divided power morphism from the divided powers on the ideal I to the divided powers on the ideal I plus J. And since everything is symmetric, the same thing is going to hold for the ideal J. Okay, so we have divided powers on sum of ideals. Okay, so for the next few minutes of the talk, I'm going to discuss a little bit about the construction of the divided power envelope, but I'm not going to get into much detail here. But I want to give you at least the the universal properties that I promised you at the beginning. So we have to start by talking about the universal divided power algebra. So for this, the setting is that we have some ring R, some commutative ring R, we have an R module M. Then the claim is that there exists a divided power algebra gamma Rm, gamma R plus M, gamma. So this is the ring, this is the ideal, this is the divided powers. And then there's also some R linear map from the module M to this ring gamma R of M, satisfying this universal property. So the universal property is that if you take any other divided power algebra Sj delta over the ring R, and you assume that you have an R linear map psi from M to the ideal J, then there is a unique divided power morphism from this universal divided power algebra to this power algebra Sj delta, such that these maps commute. Okay. So yeah, so there's a lot to unpack here, I guess. So if you want to formalize this, first you have to define these rings, because that's the way that the proof of this theorem is done by Robbie. He actually constructs the ring that satisfies this property and the corresponding ideal and the corresponding divided power structure. So that's what we are doing. And then once you have defined all of that, you have to prove that this satisfies this universal property. Okay. Also, it is very important for the proof, and this is something that we have already formalized, that this ring gamma R of M that we are defining here is a graded algebra. So the way this works is that the degree 0 part of this ring is going to be isomorphic to R. The degree 1 part is isomorphic to M. And then the positive degree part is actually this idea that appears in this divided power algebra. Okay. So constructing this is the hardest part of the proof. Defining the ring is easy, and actually I'm going to show you the definition in the next slide. So defining the ring is easy, defining the ideal is fine, but proving that this ideal has divided powers, this takes a lot of work. So I'm not going to discuss that today, but I'm going to show you the definition of this ring. So to define the ring, you have to start by considering the multivariate polynomial ring in an infinite number of variables. So these variables are going to be indexed by the natural numbers and by the module M. And then the divided power algebra is going to be some quotient of this polynomial ring in an infinite number of variables. So to get the quotient is going to be, we are taking the quotient by the ideal generated by this relation. And in this relation, we have to impose 4 conditions. And these 4 conditions, again, you might recognize some of the formulas that appear in the definition of divided powers. So in the first condition, we are asking that x0a has to be related to 1. So this is related to the property that gamma 0 of x has to be equal to 1. Then these 3 properties are corresponding to the properties for scalar multiplication, multiplication, and addition. Okay. So so continuing with the example of the sum, which is the example that I have talked about more today, we are asking that the variable x n a plus b, so here n is natural number and a and b are elements of the module. This variable has to be related to the polynomial given by taking this sum. So this is the sum over k1 and k2 adding up to n of the variable x k1a and the variable multiplied by the variable x k2b. Okay, and then similarly, you write down the properties for scalar multiplication and for multiplication. So we need to impose all of these relations to have any chance of getting a divided power structure on this ring. then the divided power envelope is going to be constructed starting from this universal divided power envelope. So let me tell you the theorem that we are trying to prove for this. So we are starting with a divided power algebra A-I gamma. And we are also considering an ideal J in some A-algebra B. Now, the claim is that there exists a B-algebra D gamma. So this dB gamma is the divided power envelope. And this algebra comes with a divided power ideal, J prime omega, that satisfies several properties. So the first property is that if I look at the ideal generated by J in this divided power envelope, that has to be containing J prime. Second condition is that the divided power algebra, the divided power structure omega is compatible with gamma. So this is the divided power structure that we started with. And then finally, it has to satisfy the following universal properties. So we started with this data of A and B, and then we are also going to take any divided power algebra CK delta, and we are going to assume two things. So first, the image of J is containing K. Second, this delta is compatible with this gamma. Well, then the universal property is the claim that there is some map from the divided power envelope, some divided power morphism from the divided power envelope to this CK delta that makes this diagram commute. Okay, so in this slide, I'm showing you how we formalize these universal properties of this commutative diagram here. So we call this ISDP envelope because that's the universal property that the divided power envelope satisfies. So we start by declaring all of the objects that we have. We have A, B, and D. These are the rings. I is the ideal on A. HI is the divided power structure on this ideal. Then J is an ideal on B. J prime is the ideal on D with divided powers. And then we have some morphism from B to D such that we have this inclusion. Then we need to introduce C's, that is done here. So for every ring C, which is an algebra over B and an algebra over A, and any ideal K in this ring C with divided powers, such that we have, again, the inclusion of ideas and we have the compatibility condition. Well, the claim is that there exists a unique divided power morphism between J prime and K, making the diagram commute. Okay, so this is just writing down this commutative diagram in B. And then what we do in our project is we define some concrete ring that we are calling DP envelope. So for us, this is going to be some concrete quotient of the divided power algebra. So we have to define some ideal. Again, this is some ideal generated by some relations, which I am not showing here today. But this is something that we have formalized. And then the divided power envelope is the quotient of the divided power algebra by this ideal. Then we have to prove that this explicit construction of the divided power envelope actually satisfies the universal property. And this is mostly done, but there's still some solids in this proof. Okay. Okay, so this is essentially everything that I wanted to discuss today. So the upshot that I want you to take from this talk is that definitions in number theory or in mathematics in general can be extremely complicated. And it is very often the case that you don't care about the concrete definition, you only care about the universal property that this definition satisfies. This is certainly the case most of the time when working with the divided power envelope. So people using the divided power envelope are not using the explicit construction, they are using the fact that it satisfies this universal property. However, if we want to be able to formalize that kind of mathematics and mathematics using these results, at some point we have to formalize the explicit definition, and we have to prove that the explicit definition satisfies the universal property. And that's what we are doing in this project. So we are doing the hard work of defining the universal divided power algebra and the divided power envelope. Okay, so thank you very much. As I said, all of this is ongoing work, but you can see how far we have gotten. Everything is publicly available on this GitHub repository. Now, if you have any questions, I'm very happy to answer.
Yeah, thank you very much for that talk.
Thanks.
Do we have questions right away? Okay, then I'll ask a question. So for finding these divided power structures, you have like almost 10 fields. Does it not become very cumbersome at some point when in every proof or sort of construction you need to provide all these fields? Do you have some convenient way of doing this when there are sort of obvious proofs for all these steps?
Yeah, with questions. So you are saying,
yes.
Let me see if I understand correctly. So you don't. So when in some cases you don't need to provide everything, right? Like you in some cases you are just assuming that you have divided powers and you don't have to prove anything. But it is true that if you want to prove that you have divided powers on some ideology, then you have to prove yes, like 8 properties, I guess. We have in some cases some simplification lemmas that say like if you can prove maybe like 4 of these properties, then the others are automatic. But yeah, like if you're constructing this, yeah, sometimes you have to provide the proofs. But usually some of the proofs are easy. Like at least the first ones, like this d power 0, d power 1, d power m, these tend to be quite easy. The ones that tend to be more annoying are the addition property and also this composition property. This can get annoying. Yeah.
That makes sense.
I had a quick question. I know you explained this, but I just don't think I quite understood it properly. But it was, why did you not actually have it as the ideal in the first argument? Like you're dragging along the alpha and then just requiring it, that dp null here, basically is what I'm asking about, d power null. Why do you do it like that rather than, for example, having the function take as an argument a proof that x is a member of the ideal and then just only operating on this? Like, I can't quite see why it was useful to have it be more general.
So I'm not claiming that it is more useful, I'm claiming that it is more convenient. So if you, I mean, if you do it as you suggested, that's kind of equivalent to like starting with the ideal here, right? Like, or you could do as you say, like put an element on the ring and then put the proof that this element is in the ideal. But then you will have to provide this proof all the time, right? Like the proof that the element is in the ideal. So we experimented a bit and we found that for us, we think that the most convenient thing is to define it from A to A. And then, I mean, this d power null is just there for like technical reasons. Most of the time, we are going to apply the properties to elements that are already in the ideal, so we don't particularly care.
So it's just to simply not require to prove that x is a member of the ideal all the time. Just to make. Okay, thank you.
Yep.
Do we have questions online? Okay, it doesn't seem so. I have one last question. Some of the papers you cited, they had French titles, so I assume the papers are in French. So is your lean formalization now the only or the first English record of that mathematics?
Yes, so for this, for the construction of the divided power algebra, the only complete reference are these papers by Rome, which are in French. Yes.
Okay.
So our formalization is going to be the second complete reference in the literature. In particular, it's going to be a reference in English, I guess. And maybe I should also mention that in our formalization, we are going to fix one issue that appears in this paper of Robbie. So this paper of Robbie, one of the lemmas here is incorrect, actually. You can fix it later, so you can rework the proof later so that you are not using this lemma anymore. But our formalization will fix this.
Okay, cool. Do you also have a blueprint that has all the details of the proofs, or do you start with the radical papers?
We have plans to create a blueprint, but we don't have a complete blueprint at this time.
Okay.
We have like a very sparse blueprint. We have only a few definitions.
Yeah, cool.
But we plan to write this up at some point and like explain the formalization.